Hello everyone. So we have come today to the week 4 course of Physics Basics. In the week 4 course, we are going to study about heat, temperature and electricity. First, let us recap our previous session. Last week we have learned about what is energy. Energy is the capacity to do work. Also, we have learned that energy of a moving object is defined as Ke is equals to half mv square, where Ke is kinetic energy, m is mass of the body, and v is the velocity of the body. We have learned few facts that when the resultant force has a tangential component, the speed changes and thus the kinetic energy changes. We always know if the speed would change, then the value of v would definitely change, and so will be the kinetic energy. So, thereby, this fact comes as when the resultant force has a tangential component, the speed changes and the kinetic energy changes. The another fact we have found out that when the resultant force is perpendicular, the speed will not change and the kinetic energy would not change. We got to know that if the force is acting perpendicular to the velocity, then velocity of the object will never change. And since the velocity of the object will not change, the kinetic energy would not change. We can refer to this formula for understanding this. We have also read that work done is equals to force into displacement, that is Ft into dr. We have generally termed this force as Ft due to tangential component of force, thereby Ft is tangential force. The SI unit of work done is joule, which is represented by capital J. Although work done unit can also be written as Newton meter. The unit of force is Newton, the unit of displacement is meter, thereby multiplication of Newton meter. Here we have represented work done as dk, that is change in kinetic energy. We have also learned about work energy theorem. Thereby we have learned that work done on an object by the resultant force is equal to change in its kinetic energy. The work energy theorem can be stated as the change in kinetic energy is responsible for work done. Here we have represented the same. dk is k2 minus k1 or kf minus ki, where kf is final kinetic energy minus ki is initial kinetic energy. Thus, final kinetic energy minus initial kinetic energy, that would be equal to work done. The same is represented by work energy theorem. Also, work done on different objects of system by internal forces may not be zero. This was the another fact we have learned previously, that the work done on different objects of system by internal forces may not be zero. That means internal forces could also cause some kind of work on the system. Further, we got to know about power. Power is rate of doing work, where mathematically it can be expressed as dW by dt, that is work done per unit time. Deriving this equation, we get power is also equals to Fv, where F is the force and V is the velocity of the object. The SI unit of power is watt, and generally another unit of watt is also used, that is called as horsepower, where 1 HP, that is 1 horsepower, is equals to 746 watts. Further, we have studied potential energy. It is the energy that is stored in an object or system by virtue of its position or arrangement of parts. We have also learned the kinetic energy of an object remains same before collision and after collision, and thereby we have come to the formula of conservation of mechanical energy that states that if the work done by the external forces on the system is equals to EF minus EI. That is, conservation of mechanical energy states that work done by the external forces would always be equals to final energy of the system minus initial energy of the system. And at last, but not the least, we have learned that mathematically conservation of momentum can be written as m1u1 plus m2u2 is equals to m1v1 plus m2v2. That is, momentum before the collision and momentum after the collision remains same, where m1 and m2 are the masses of object 1 and 2, and u1 and u2 are the initial velocities of object 1 and 2, whereas v1 and v2 are the final velocities of object 1 and 2. Next, we are going to study the table of contents of today's lecture. Today's lecture contains the following contents: hot bodies and cold bodies, heat and temperature measurement, heat transfer, electricity, current density, electric field inside a conductor, drift velocity, Ohm's law, temperature dependence of resistivity, superconductors, battery and EMF, Joule's law of heating, Faraday's law of electrolysis, Kirchhoff's law, and combination of resistors. The learning objectives of this week would be temperature and its measuring units. We are going to learn what is temperature and what are its measuring units. Also, we are going to know what is heat and how heat transfer takes place. Further, we are going to know the calculation of heat transfer on combination of conductors. That is, when the heat is transferred, then how it is calculated. And when the conductors are combined or attached with each other, how heat transfer takes place and how heat transfer can be calculated on that case. Defining electric current and current density, how electric field work inside a conductor, the dependence of Ohm's law on temperature, and last, the calculation of equivalent resistance on combination of resistors when they are connected in series and in parallel. So starting our today's lecture with hot bodies and cold bodies. Hot bodies and cold bodies. When the hands are rubbed for some time, they turn warm, isn't it? Let's take another example. When the grinding process is done on a part, the part becomes warm, or I must say it becomes hot. Let's take another example. When an aeroplane crashes, it becomes so hot that it catches fire. The next example we can take is, if the same heat energy is provided to a container, then rise in temperature of a container with lesser water will be seen, and the container with more water, the temperature would not rise that much. So, what we can conclude from the previous slide is that cold bodies absorb energy to become hot. As we have seen in the previous slide, that when the hands are rubbed for some time, they turn warm. Thus can be concluded, cold bodies absorb energy to become hot. The next thing that can be concluded is, hot body has more internal energy than a cold body, because those internal energy can be transferred while they are in contact. The next thing that can be concluded is, when any hot body comes in contact with a cold body, the result is the cold body warms up and the hot body cools down. That is, whenever a hot body comes in contact with the cold body warms up because there is a transfer of energy from hot body to cold body. Further, we are going to study about heat and temperature. Defining heat and temperature. So what is heat? Let's study in this slide. The non-mechanical process involves transfer of energy from a hot body to a cold body. Heat can be defined as the energy transferred from one body to another without any mechanical work involved. So, as the statement says, there will be a transfer of energy. So, heat is a kind of energy, but there will be no mechanical work involved in that. Thus, the definition of heat can be redefined as the energy transferred from one body to another without any mechanical work involved. This is because heat is a kind of energy and therefore its measuring unit is joule. What is temperature? Temperature is the measurement of hotness or coldness. It can be measured in various units like Fahrenheit, Celsius, Kelvin, or Rankine. Temperature indicates the direction in which the heat energy will flow, that is, from a higher temperature body to a lower temperature body. The next thing we are going to learn is Zeroth Law of Thermodynamics. The Zeroth Law of Thermodynamics states that if two bodies A and B and A and C are in equilibrium, then body B and C are also in thermal equilibrium. Thus, all the bodies in thermal equilibrium should have same temperature if they are following the zeroth law of thermodynamics. Otherwise, a heat current will always flow from hot body to cold body, as we have learned earlier, that heat always flow from hot body to cold body. The next thing to cover today is temperature measurement. Let's take the mass of mercury in a glass bulb terminating in a long capillary tube, such that the mercury column length in the capillary tube changes with the temperature. That is, the each length corresponds to a temperature of mercury. Let me try to explain this to you again. Let a mass of mercury is placed in a long capillary tube, where the mercury column length in the capillary tube changes with temperature. Let T1 be the temperature of the ice point and T2 be the temperature of the steam point. Thus, when mercury is placed in an ice point, the column length will be L1. Similarly, when the mercury will be placed at the steam point, the column length will be L2. These are the assumptions. When the mercury will be placed in the ice point, then column length will be L1. And when the mercury will be placed in the steam point, then the column length will be L2. We are assuming a linear relation between the temperature and the length of the mercury. Thus, from the mathematics, we already know that if there is a linear relation, then the equation is like y is equals to mx plus c. This is the equation of line, and we are going to inherit this equation here also. Thus, T is equals to Al plus B, where T is the temperature, L is the length of the mercury column, and A and B are constants. Or if we refer to the mathematical equation, A is equals to m, that is the slope, and B is equals to a constant. Let's suppose y equal to mxc is equation 1. Further, change in 1 degree of temperature reflects as a change of L2 minus N1, change of L2 minus L1 divided by T2 minus T1 in the mercury column. As we have studied earlier, that change of temperature would reflect in change in mercury column. So, howsoever is the change of temperature that is in the denominator, same will be reflected in the length of the mercury column that is in the numerator, since both are directly related. The centigrade system assumes that ice point is at 0 degrees Celsius and steam point as 100 degrees Celsius. These are the standards that a centigrade system follows. Let L0 0 degrees Celsius in mercury column and L100 100 degrees Celsius in mercury column. This means L0 is the ice point, L100 is the steam point, and so is their temperature. 0 degrees Celsius is the temperature of the ice point, 100 degrees Celsius is the temperature of the steam point. Putting these in equation 1, that was T is equals to Al plus B, we would get the following results. When the temperature is 0 degrees Celsius, here we can put T is equals to 0. Further, we have believed that A is a slope and we are keeping this same here as well. L0 is as per the 0 degrees Celsius, that is length of the mercury column obtained when it is placed at the ice point. So L will be equal to L0 plus B. Let's B be the constant as we have studied in the equation of line earlier. I repeat, 0 is the temperature at ice point, A is the slope, L is equals to L0, that is length of mercury column at 0 degree temperature, and B is constant. Thereby, by reshuffling, we get that B is equals to minus of Al0. Let's denote this equation as equation 2. Further, putting another case in this equation 1, that is equation of steam point, we will treat temperature as 100 degrees Celsius for the temperature of steam point and L equals to L100. That is, L100 is the length of mercury column when it is placed at a steam point. Rest everything remains same. A is the slope and B is the constant. By putting equation 2 in equation 3, we would get A is equals to 100 L100 minus L0. How this has came? We have just put the equation 2 in equation 3. Equation 2 was representing the value of B, that was minus of AL0. When we place that value of B, that is minus of AL0, in this equation, we must have received 100 equals to AL100 plus minus of AL0. Taking A as common and shifting it to left hand side, we would get A is equals to 100 into L100 minus L0. Let's denote this equation by equation 4 and put this equation 4 in equation 1. Thus, we would get T is equals to L minus L0 into 100 divided by L100 minus L0 degree. Another popular measuring system is Fahrenheit system, where the ice point of the Fahrenheit system is believed to be at 32 degree Fahrenheit. I hope you remember of the ice point of the degree Celsius system. That was at 0 degree Celsius. Ice point of Fahrenheit system is at 32 degree Fahrenheit. Similarly, the steam point of Fahrenheit system is at 212 degree Fahrenheit, whereas the steam point of degree Celsius system was 100 degree Celsius. Thus, by making out a relation between the Fahrenheit and centigrade system, we concluded a conversion formula to convert any unit from centigrade to Fahrenheit. That is, F is equals to 32 plus 9 by 5 into C, where F is the value of temperature in Fahrenheit and C is the value of temperature in degrees Celsius. Thus, if we put the value of temperature in degrees Celsius in right hand side and we solve this equation of right hand side, we will definitely get the temperature at Fahrenheit at the same point. The next thing we are going to study is heat transfer. There are three different methods for heat transfer: conduction, convection, and radiation. Let's start with conduction. The temperature of other end of the metal rod increases when one end of the metal rod is placed in the heater. This transfer of heat is due to the molecular collisions. This process of heat transfer is called thermal or heat conduction. Okay, so let's try to understand this using a picture. This picture perfectly denotes a rod. Let's suppose there is the one end of the rod is placed in heater. Let's suppose T1 is the temperature of the heated end and T2 is the temperature that is of the ideal state. So there will be a transfer of heat from T1 to T2 and T1 would always be greater than T2. This transfer of heat happens due to the molecular collisions. Those molecules are present inside this rod, and this process of heat transfer is called thermal conduction or heat conduction. Next thing we are going to study is thermal conductivity. The thermal conductivity of a material is its ability to conduct heat. The SI unit is joule per second per meter per Kelvin. In short, it can also be written as watt per meter per Kelvin. Consider a rod of length x and cross-sectional area A. So this is the rod that we have to consider. The length of the rod is x. The cross-sectional area of the rod is A. So let the temperature of the ends of the rod is T1 and T2. This is T1, this is T2. The following assumptions are made before going ahead. The rod surface is covered well by the non-conductive material. That is, the complete surface of the rod that we can see here from between the ends, it is been completely covered by a non-conducting material. Therefore, heat transfer to the outer environment is zero. Thus, no heat can be transferred from this surface area. After reaching steady state, at any given cross-section, the rod transmits equal amounts of heat per unit time. This statement indicates that when a steady state is reached in the system, there comes a time that every cross-section of the would emit equal amount of heat per unit time. That is, the heat transfer that is going to take place from T1 to T2 is going to be equal per unit time in steady state. If del Q is the heat passing through the cross section in time del T, then heat current is defined as del Q by del T. If we suppose del Q heat is transferring from a point through a cross section and it has been transferred in the time del T, then heat current is defined as del Q by del T, where the unit of heat current is watt. At steady state, heat current is proportional to area of cross section. That is, del Q by del T would be directly proportional to area. Therefore, larger will be the area, larger will be the heat current. Heat current is del Q by del T. And if smaller is the area, smaller will be the heat current, which is del Q by del T. Also, we can figure out that heat current is proportional to temperature difference, that is T1 minus T2 between the ends. If del Q by del T is directly proportional to T1 minus T2, this has been written here and this has been mathematically expressed here. Also, we can make out that heat current is inversely proportional to the length x. Del Q by del T is inversely proportional to x, that is del Q by del T is proportional to 1 by x. Converging all three equations, we can write del Q by del T is equals to K into A into T1 minus T2 upon x, where we have known del Q by del T is directly proportional to A. We have studied in the previous slide. Here, del Q by del T is directly proportional to T1 minus T2. We have studied in this here. Further, we have studied del Q by del T is inversely proportional to the length x. Here, in this equation, K is a material constant or also called proportionality constant, or it is also known as thermal conductivity of the material. Thus, here we close our session 1. Thank you.